All right, so let's get started. We're going to be covering section 4.5 today. And this is actually the last section that will be covered on exam 3. Or sorry, yes, 3. Okay, so let's maybe just write that down in case anybody is late to class today, that this is the last section on exam 3. Okay. And so all the exam dates should be on that course schedule. They should also be on Canvas. And so, yes, it should be on Friday the 16th. So it is not this week. Don't worry. This is not a surprise. You have a test in 2 days. It is next Friday. Okay. So we'll have at least a week to kind of digest this material and really hone our understanding of it before we move or before the exam. Okay. Maybe let's write that down too in case anybody else is having that same question. So this will be Friday, April 16th. Okay. There is one more section in chapter 4 that we'll be covering, but we're going to lump that in with the next chapter because I think it just makes more sense there. And there are some chapters that we skipped, not chapters, there are some sections from chapter 4 that we skipped, and that's okay. I think we spent time on the things that were valuable, the things that tend to come up more often, but there are blank notes on Canvas in case you have the desire to go over that content on your own time, okay? All right, so 4.5, today is all about derivatives and how they impact the shape of the original graph. Okay, and so let's maybe add that on here that we're looking at the shape of a graph for the original function. Okay. All right, so we're going to do our what we know and what's new in a slightly different way. Today, we're actually going to answer some questions for our what we know, and then we're going to take a look at a similar kind of question for what's new. Okay, and so let's take a look at this graph right here. All right, and so we're gonna do a little throwback in our brains to when we were looking at Franklin, the turtle, and how Franklin was moving either on the beach towards the water or towards the grassy part, and that's really what we're imagining here. Okay. And so in this case, we're taking away all the fun things. We're just focusing on the motion. All right. So consider a particle is moving along the t-axis with the function s of t equals 2t cubed minus 14t squared plus 22t minus 5. Okay. And we're only looking at this over the interval from 0 to 5. Okay. Now, a question that we can maybe take a look at is this. I'm wondering, when is the particle moving to the right? When is it moving to the left? And when is it at rest? Okay, and we're going to look at this first graphically. So just from the picture, how do we know when something is moving to the right, moving to the left, or at rest? Okay. So I'll give you a few moments to think about that. Maybe go back into your old notes, all the way back in chapter 3, and move to the right, to the left. Okay. All right. So we've got one idea in the chat that positive y values is right. And we have sort of a similar idea that the slope is what we're looking at. So let's think about that for a moment. Are we looking for slope or are we looking for the y values? Now, it turns out when we're looking for the direction of travel, okay, so direction of travel means that we want to look at the first derivative, okay? So when we're looking for the direction of travel, like moving to the right, that means that we have a positive slope, all right? We're looking to move to the left, we're looking for a negative slope. And if it's at rest, then we're looking for when that slope is 0, okay? Now, if we kind of look at this graph a little bit closer, let's take a look at some regions where there's a positive slope, okay? So moving to the right will be a positive velocity, which on this graph, on S of t is positive slope, okay? And so if we were to think about when there is a positive slope, we might say from here all the way to here. Sure looks like positive slope to me. And where else on this graph might we be able to describe that there is a positive slope? Yeah, from like x equals 3.5, somewhere in there, right? So like this whole part is also a positive slope, right? So positive slope means we're looking to the right, but only when we're looking on the graph of position, okay? That last part is so important. What we're saying right now, positive slope means moving to the right, is only true when we're looking at a position graph. And if we were to actually write the intervals out, we could say from 0 to 1. All right, so we're including 0, but we're not including 1 in union with, and we could say maybe 3.5 all the way to 5, and we're going to include 5, but we're going to leave out 3.5. Okay. All right, so let's do something similar, but for moving to the left, right? So moving to the left, how would I change the statement that I wrote here? Yeah, so we're looking for slope is negative, but let's say first maybe negative velocity, which on S of t is negative slope, right? And if we were to highlight the corresponding section on our graph, we might say from here all the way down to here. And so in interval notation, we would exclude 1, and we would go all the way to 3.5, but we would also exclude 3.5. Okay. Let's zoom out a little bit. We've got the positive slopes is where we find positive velocity. And the negative velocity is going to be negative slope, but only if we're looking on the position graph. So let's finish this off. Where is this particle at rest? Right? Where is this particle at rest? Okay, so 0 velocity. And on the position graph, is zero slope. Okay. And where might those be on this graph? Give me some t values that correspond to that. X equals 1, x equals 3.5. Good. So we've got up here, all right? And down here, we would predict that we would have a horizontal tangent, right? And if we sort of sketch that in, we can see those are horizontal tangents. And so at rest means that we have a zero slope, but only if we're on the position graph. And so we can say here that t equals 1 or 3.5. Okay. So that's what we learned back in chapter 3. All right. And if that wasn't something that we remembered, hopefully this is something that we remember now. Okay. But there's sort of a second part to this question, which is we can look at this as a graph and find these answers. But I'm wondering if you can describe to me how we would find this algebraically. Okay. Because in this case, sorry for moving the screen up and down so much, we have an actual function. So it is possible that someone could ask you the same question and not give you a graph, but you would still be able to get to the answer. Okay. So take a moment and think about that. How do we use just the equation to get these same values? All right, so here's our position function. How do we find, maybe let's just say, how do we find out where it's at rest if we just have the position function? Okay, I like this. I like this. Yeah, we have an interval given, right? And exactly, gosh, we've been doing this for a while. Take that derivative, set it equal to 0. Huh, must be something that's an important idea, okay? And so if we wanted to find out when something is at rest, so we could say, at rest, v of t will equal 0. Okay. So at rest, v of t is going to equal 0. And so let's go ahead and find our v of t. All right. And I think Antonio already put that in there, that v of t is equal to s prime of t, or the derivative. And so thank goodness, no chain rule, no fraction powers, it's just power rule all the way through. Okay. And so when we take that derivative, we'll end up with, let's see, 6t squared minus 28t plus 22, and then a minus 0 at the end. Okay. Now here's my derivative. So I'm going to set that equal to 0. Because if I can find out the t values that make this 0, then I know when the particle is at rest, okay? And so in our continuing in our theme, we've got our particles at rest when that velocity equals 0. All right, so now let's do the algebra part. This looks like some big numbers. I know I probably should factor, so let me see if there's a greatest common factor I could pull out first, okay? And I notice that I can take a 2 out and I'll get 3t squared minus 14t plus 11. equals 0. Well, the smaller numbers are definitely nicer. And now I can divide both sides by 2. So I've got 3t squared minus 14t plus 11 equals 0. Okay. And now let's try and factor. So I'll give you a moment to factor that. Now, factoring, I will say, is a skill that I have used in probably every single math class that I've ever taken. All right. And I would expect that you would have a similar experience. And most of the time, that first number is not going to be 1. Okay. And so it would be really important, if that's something you're still not feeling super confident with, spend a little bit more time with that and, you know, see how you can make it a strong point for yourself rather than a place of challenge. Okay. All right. Anybody got that factored? If you do, maybe type that into the chat. T minus 1 and 3t minus 11. Can anyone confirm that for us? Or not confirm it? That's fine. Happens. Let's maybe get one more person to see whether this is correct or not. It's that awkward moment where we're all hoping someone else is going to do it. All right, there we go. Excellent. So we've got t minus 1 and 3t minus 11. Excellent. All right. Now let's go ahead and finish this off. We can say that t minus 1 equals 0 and that 3t minus 11 equals 0. Ah, this is nice. We've got t equals 1 as one of our answers, which makes sense because that's what we said from the graph, right? And that's where we had a slope that was horizontal, right? Now, I actually appreciate that in the beginning, Thea was like, oh, I don't know, it's like 3.5-ish, right? Somewhere in there. And that's sort of the tricky part about graphs. It's like sometimes you know sort of roughly where it is, but if you needed an exact answer, that's what we can use the algebra part to really support. So we can add our 11 to both sides. We can divide by 3. And we'll get 11/3, which is roughly 3.5-ish, give or take a little bit. And so it seems like our algebraic answers support our graphical answers. Okay. And so this example right here, I think, is really powerful in the sense that we can look at a graph, we can think about what we're looking for, and we can also use algebra to support our results from the graphical one. Okay. So what's new? Today is the day where we will finally get to figure out, but how do we know which direction it's moving? Like, is it going to the right? Is it going to the left? Who knows? Okay. So today is the day we're going to answer those questions. Now, before we get there, let's take a look at what's new, okay? And so we're going to work through some questions here, but this time, and this is the most important thing to, let's go with like hot pink. This is the most important thing to read in the directions of anything that comes with a graph. Okay, this is a graph of velocity. We are not looking at a graph of position anymore. This is a graph about velocity, okay? And so what that means is that when we answer things, we want to think more about what this means and less that we're looking for a certain thing on the graph, okay? Because now the graph is different. And so let's talk about question A here, okay? So here's a graph of velocity. Now, question A says, what is the velocity of the particle at t equals 2? And separately, what is it at t equals 7? And explain how you know, all right? So if I want the velocity at 2, on a graph of velocity, okay, so on v of t, this is the y value of the graph. Okay, this is the y value of the graph. How come it's the y value of the graph? Yeah, that's what's on the x-axis, right? I know we're talking about like some complicated things, like we're looking at y values and sometimes we look at slopes, but it goes all the way back to like the first time you ever saw graphs in, I don't know, elementary or middle school, and your teacher probably said like, you have to read the axes, like you have to know what it's talking about. And this is exactly the moment where we really have to know what we're looking at, okay? And so since this is the y value of the graph, because we're looking at velocity, we can just say that v of 2 is 3. Okay. Now, similarly, if we were to write a sentence on v of 7, we could say on v of t, this is the y value of the graph. And so can someone maybe type into the chat what v of t is for this particular graph? Exactly, very nice. So we've got a y value of -1, okay? And so let's see, maybe we do this. And so v of 2 is 3 and v of 7 is -1, okay? All right, let's take a look at this second question, all right? When is the particle moving to the right? When is it moving to the left? And explain how you know, all right? So I'm gonna go ahead and go back up here for a moment. And let's take a look at something we wrote down earlier. We said that something is moving to the right when there is positive velocity. All right. So something is moving to the right when there's positive velocity. Now, the rest of what we wrote down earlier was only true when we were looking at the position graph. So I'm wondering if someone can tell me what positive velocity looks like. Oh God, what positive velocity looks like on a graph of velocity. I have one answer that says positive slope. Okay. So is it a positive slope? Positive y value? I think those are two really great ideas. All right, well, exactly, okay. Now this graph is a graph of velocity. So where is there positive velocity that's secretly saying, where is there a positive y value? Okay. This is perhaps the number one mistake, is that anytime someone says velocity, students sort of skip over that middle part and they're like, velocity means positive slope, right? But that's only true if we're looking at a position function, all right? And so on this graph, let's make sure we pick the right color here. We're looking for a positive y value. And so that would include everything that is up here, but it would not include at 0 and at 6, because at those places, what is the velocity at these two places? Yeah, velocity is 0. So we want to exclude those from our answer. So we'll say parentheses 0 all the way to 6 and close it with a bracket or with a parentheses. Okay. Your explanation could be very similar to what you said up here, that we're looking, that velocity is the y values. So positive velocity means positive y values. Okay. We can grab our similar statement from above, that left means positive, or left means negative velocity. We're not looking for negative slope.
Professor?
Yes. Yes. Yeah, I think you might be muted. Okay, well, I'm happy to answer your question in a little bit. All right, so moving to the left, we want to think negative y values because this is a graph of velocity, and we do not want to make the mistake that we're looking at negative slope. Okay. And so on our graph, we can say that that's this piece right here, and we can write it as 6, 8, both in parentheses. Okay. All right, let's pause here. Whoa, let's pause here for a moment. Are there any questions so far on part A and part B? Because it's weird.
I have a quick question.
Absolutely. What's up?
Also, sorry if my mic spazzed out earlier. My internet was
That's okay.
going insane.
It happens.
So for the graph before this one, we were looking for positive velocity and negative velocity because it was the slope, right? And that's
in both
how we were determining.
In both cases, we're looking for positive velocity. Like right still means positive velocity.
Right, but this is a graph of velocity and the other one was a graph of
Position.
distance, position.
Yeah.
Okay.
Yeah. So because this is a graph of position, we want to look for slope. But if it's a graph of velocity, we look for the y value.
Okay, cool. That was my question. I just want to make sure that I had it down correctly. Thank you.
All right, I see something in the chat. Velocity is change in magnitude and direction. Yeah, exactly. So you can go in a direction and be going slower in that direction, but still be going in that direction. Okay. So when my dog likes really long walks, and every time we get close to the house, she slows down. I'm like, are you kidding me right now? We just went on like a few mile walk and you're just going to slow down. We're still going towards the house, but she's just really, really slow. Okay. All right. So take a stab at question C. When is the particle at rest? And explain how you know. So type some ideas into the chat. What do you think about that one? Oh, right. Yeah, I like this. I like this. Okay. So we can say, similarly to what we did up there, that a particle is at rest when there is zero velocity. Okay, so that doesn't change, but we're not looking for zero slope. We are looking for zero as a y value. And I see your question, Marissa. Give me 1 second. At rest, we're looking for the zero y value. And we are not looking for zero slope on the velocity graph. Okay. Now, Marissa, you ask a really great question, which is why do we have brackets there? And that is because if we look at this graph here, all right, and I ask you, what is V of 8? You would tell me that V of 8 is 0. And if I asked you what V of 0 was, you would also say 0 because those are the y values there. But when I'm looking for whether it's moving to the right or the left, it has to be a positive value or a negative value. And 0 is not positive and it's not negative. And so that's why we don't include those. Does that make sense? Okay. So the graph of position is a physical representation of how a particle moves. Yes. And the velocity graph is more abstract because it's describing how, like, yes, how quickly that thing is happening. Yeah. Okay. Great. All right. So I think from our graph above, we've got t equals 0, 6, and 8 as our places where that particle is at rest. Okay. And again, that's because we've got this point has a y value of 0, this point has a y value of 0, and this point has a y value of 0. Okay. All right, so we've got one last question here, which is when does the particle have positive acceleration? Okay, so we haven't talked a ton about acceleration. And I'm wondering if someone can remind me of how acceleration fits into position velocity. Okay, so acceleration is the derivative of velocity. Okay, so that's an important concept to note here, that if we just look at acceleration, that is the derivative of velocity. We might also say that is the slope of velocity. Okay, and so if we're looking for positive acceleration, we are looking for a positive slope on v of t. Okay, so we're looking for a positive slope on v of t. Anytime that happens, we're going to have positive acceleration. Okay. Now, if we change this statement to say, I'm looking for negative acceleration, and I'm looking for a negative slope on v of t, okay? And if I'm looking for zero acceleration, I'm not moving any faster or slower, but I'm just cruising along at a constant velocity, that might mean we're looking for zero slope on v of t, okay? And so if we go back up to our graph, let's think about where we might see positive acceleration. All right, and I'm keeping in mind we're looking for positive slope. And let's similarly look for, what color have we not used yet? Use that one. Negative acceleration would mean that we're looking for a negative slope. Okay, and so if we go back up to our graph, if I'm looking for a positive slope, which regions have positive slope? Exactly. Yep. That would be one region, and 7 to 8. Perfect. Great job, folks. And so if we sort of highlight this part, I probably should have picked bolder colors, but that part right there is going to have a positive slope. That means the particle is accelerating. It has a positive acceleration from 0 to 2. And it has a positive acceleration from 7 to 8. Okay. And if we want to take a look at the negative acceleration here, we could say negative acceleration is here and here. So that whole region has a negative slope. Okay. So if we write down our answers, we could say there's a positive slope from including 0 all the way to 2, but not including 2, in union with 7 to 8, and we include 8 because the slope is still positive there. Whereas that negative slope, well, where does that happen? It happens at 4, and it goes all the way to 7. Okay. Now, this last question is a tricky one, I think, but where is there 0 acceleration? All right, so now we're looking for a 0 slope. So take a look at that picture. Where do we see a slope of 0 on this graph? From 2 to 4, 2 to 4. All right, I'm going to go with Graham's iteration of this, that we have it in parentheses, all right, because we have sort of these pointy corners here. And so there's like an infinite number of slopes that might happen there. So we got to exclude the pointy corners. We're just going to say 2 to 4. Okay. So from 2 to 4, we have a 0 acceleration. All right, it's just cruising along in one direction, not changing the speed at which it goes at. That is a fabulous question, Eric. What would the graph of acceleration look like? So if I wanted to graph acceleration, I could say, let me pick the slopes of each part and let me graph it. So maybe we could go like 2, 4, 6, 8. Okay. So the slope from 0 to 2, that slope looks like it's 3 halves. And so I would say this, and this would be 3 halves. I'm just graphing the slope. Okay. What would I graph from 2 to 4? Like what y value would be on this acceleration graph? 0. And so I'm going to go here. I'm going to say 2 to 4 is going to be right at 0. Okay. Now the slope from 4 to 6 is negative 3 halves. So I might go down here and have negative 3 halves. And then the slope from 6 to 7 is like negative 1, negative 1. And then the slope from 7 to 8 is a positive 1. Okay. Yes, that is a great observation, that the derivatives drop a degree. And that makes sense because when we're thinking about the power rule, that's exactly what we're doing. We drop a degree every time we take a derivative. Okay. Yes, and if you stop instantly, yes, you have to go through all of those. Exactly. Cool. Great questions. All right. I know this is on the earlier side for us, but I think this is actually a nice time to take a break and kind of think about the stuff that we've talked about. When we come back, we're going to look at some theorems. Okay. I know those aren't everyone's favorite, but we're going to learn some theorems and some processes. And more importantly, look at how much blank space there is here, because we're going to be drawing a lot of pictures. Okay. So I will tell you, pictures and words make this particular topic so much easier. All right. So write a lot of words, draw a lot of pictures. Okay. Even if you're not sure what you're doing, just draw a lot of pictures, write a lot of words. Okay. So let's do this. All righty. Here we go. So before break, we talked about graphs of position, and then we finished off with some graphs of velocity, okay? And what we're going to talk about now is two theorems that are particularly helpful in determining an answer to the question that some of us have started to ask already, which is, how do we know if something is a minimum or a maximum? How do we know if the velocity is positive or negative? What does that kind of look like? And how do we tell from an equation? Okay. And so that's really where we're headed in the second half of classes. Where do we find out the answers to these questions using only equations? Okay. Now, I know I just said we're talking about equations, and before break, I was like, we're going to be drawing some pictures too. I think that sometimes the picture drawing can support that part of our brain in connecting the dots between what we're finding numerically and what that number means, okay? So here is the first theorem. So this theorem is the first derivative test, okay? And let's read this over. Suppose that f is a continuous function over an interval that contains a critical point. All right, so we're looking at a specific piece of a graph that has a critical point. Now, just as a quick reminder, on Monday, we talked about critical points being places where the derivative is equal to 0. And so that might be a place where we have the maximum, or it could be a minimum, or there were sort of two cases where we looked at where it sort of went up and then it flattened off and then it kept going, or it was going down, it flattened off, and then it kept going. Okay. And so when we're thinking about our critical points, those are sort of the pictures we want to put in our heads, that we're looking at extrema. All right. We're looking at extrema of functions, or maybe places where they sort of level off. Okay. Now, if the function is differentiable, okay, so meaning that it's a smooth curve, then f of c satisfies one of the following descriptions. All right. So if f prime changes sign from positive to negative, then f of c is a local maximum. Roman numeral 2. If f prime changes sign from negative to positive, then f of c is a local minimum. And if f prime has the same sign, then it's neither a minimum or a maximum. Okay. I think that's a lot of words. For some people, those words make a lot of sense. For me, and I think for some other folks, it's really helpful to have some diagrams around this. Okay. So let's look at ways that we can have a local maximum. Like, how do we know if we have a maximum just from looking at an equation? Exactly. That's exactly what we're going to do. Okay. So I want to put two pictures here. One is going to be on f of x, or the position function, and the other picture is going to be on f prime of x, or the velocity function. Okay. So let's say that we have this on f of x, or s of t. So we're looking at a position function. Okay. It might look something like this. I want to draw a maximum, so it's going to go like that, like the top of an upside down parabola. Okay. And in particular, at x equals c, all right, we know that f prime of c equals 0, meaning there's a horizontal tangent line there. But let's look at the slope on both sides of that. Well, the slope on this side, tell me about this slope, positive or negative? Positive, good. So this is positive slope, or we can say that we're looking for a positive f prime of x, okay? And then for a moment, it becomes 0, but then on the other end, on the other side, we have a negative slope, or we can say a negative f prime of x. Okay. And so that's what this first bullet point is really saying, that if you change signs from positive to negative, then f of c is a local maximum. All right, so kind of marinate on that for a little bit, but hopefully that makes some intuitive sense, that when you're getting to the top of something, you're going to go up, and then when you come you want to come back down, you're going to go down. Okay. Now, because I think it's harder to read a graph of velocity, let's kind of put what this might look like on a velocity graph. Okay. So on f prime of x, or we can say v of t, here's what this might look like. Okay. So let's say that we have the t-axis here, all right, the time axis, and we're looking at velocity. Turns out that if we go from positive velocity to negative velocity, well, that means that on the original function, we had a maximum. What might that look like? I got to go from a positive velocity to a negative velocity. Anybody want to take a stab at that? Maybe sketch a picture on here, what that might look like. All right, we want to go from positive velocity to negative velocity. Oh, two different ideas. I love it. I love it. Okay. So let's take a look at, whoa. Let's take a look at, the, okay. So let's take a look at the one that has like the purple and the blue. So like, God, oh, no. So I can't see this on my screen. So I'm kind of like trying to eyeball where it is, but like, let's look at this one first. All right. So with the one that I'm highlighting in the red right now, does this go from positive velocity to negative velocity? Okay. Where's the positive part? If I undo that for a moment, where's the positive velocity part? Can someone maybe show us where that is, the positive velocity? Yeah, I would agree. There's positive velocity right here, right? Whoops. Here, this is positive. Okay. And then, because it's a positive y value, all right? So where's the negative velocity part? Yeah, okay. So here's our positive velocity. And then all of a sudden, now we're negative velocity. Okay, that seems to satisfy what we're talking about to find a local maximum. Okay. What about the other part of that parabola though? This looks like negative velocity to positive velocity. So maybe we don't need that part. Yeah. Okay. So, Ethan, I wonder, yeah, if you can delete just that blue part there. Okay. And then maybe the green parabola. I don't think we need the whole one. I think we just need part of that parabola, right? Okay. So there's a lot of ways in which it could look, but what we want to see really is that we go from somewhere in the top, that's positive velocity, to somewhere in the bottom, because that's negative velocity, okay? And so I think, Eric, you had the most straightforward way. You were like, this goes from positive velocity to negative velocity, that's absolutely fine. Okay. The only thing that has to be true here is that we have to go from a positive y value, since we're looking at velocity, to a negative y value. Okay, and so let's go ahead and sort of do this part is positive velocity. And down here is negative velocity. All right, I know it has a negative slope, but this is not a graph of position. This is a graph of velocity. So we're reading it like we're reading y values. Okay, and so maybe we leave ourselves a little note that on this one, we are reading slope, but on this one, we are reading y values. Okay. All right. Well, let's try our hand at exploring this one now. Okay. So what does it mean to have a local minimum? We're going to try and draw corresponding pictures to that. Okay. So if I want to draw, if I want to draw a local minimum, all right, the local minimum here, let's look at our two cases. All right, so we're going to look on f of x. So on f of x or s of t, and then separately, we'll look at on f prime of x or v of t. Okay. All right, now I'm asking you to draw a minimum. I think is fairly straightforward. It is very much sort of our traditional parabola, right? We're gonna go down like this, we'll get to the bottom, we'll turn around and go back up, okay? Now, where this happens, where this turning point happens, we're saying it happens at x equals c, and we're saying that f prime of, f prime of c equals 0, okay? Now, let's keep our colors the same here. I have a negative slope on this side, okay? And I have a positive slope on this side. Oh, sorry. So this is positive slope or positive f prime. And on this side, we have negative slope or negative f prime. Okay. And so the theorem says that if we have a negative slope to a positive slope, we have a local minimum. All right. What does this look like on the graph of velocity, though? Here's our t-axis, and this is the graph of velocity. All right. How can we modify our previous picture to now say, if I see this on a velocity graph, then I know that there's a minimum on the original graph. Right, and you can either draw one or you can describe in the chat what it might look like. Okay. Yeah, we're going to have sort of positive. Exactly, Graham. We're going from the negative y values to the positive y values. Okay. So I'm going to go ahead and zoom back in. Let's get that picture. So we go from negative to positive because this region is negative velocity. And this region is positive velocity. Okay. All right, so we've got our local minimum, we've got our local maximum, we've got pictures to go with it. We've even got pictures to go with it for both the original graph and the velocity graph, okay? We're gonna finish off here with this last case. If f prime has the same sign, then it's not a local min and it's not a local max, right? So if you have the same sign, it just happens to flatten out a little bit, you're going to end up with one of these two cases here. Okay. So let's draw a better picture for that. We say this is neither a local max or a local min. And what does that look like? So on f of x or s of t, and then separately on f prime of x or v of t. Okay. And on the original graph, it looks exactly like what we sketched up there. You might have a case where it goes like this: positive slope, zero slope, positive slope. Okay. And so our x equals c would be right here. And you'll notice that we've got positive slope and positive slope. All right, so it only rests for a moment in time, but it doesn't actually change direction. And similarly, we could have a case where we are going down and then flattening and then going down. And so this one, we would have x equals c, and we would have a negative slope and a negative slope. Okay. I think what makes this one a little trickier is, what does this one look like on the derivative graph? Okay. Now, let's draw a few different options. This or this or, okay. So we'll draw a couple options, but what might something that has a positive slope to a zero slope to a positive slope? Let me say that again, but replace the word slope with derivative. Positive derivative to zero derivative to positive derivative. Okay, now ask that we keep both those options up there here. When we're looking for y values, right? Because now we've moved on to a velocity graph. Everything we're drawing on this right-hand side should be talking about the y values. So we're saying we want a positive y value to zero to positive y value. Okay. And so for that reason, we're going to get rid of the green line, but we can keep the red one, because if we look at the red curve, we have everything is positive y values. Okay. What might it look like if we want to say, I just want negative y values to zero to negative? Nice, nice, good, good, good. Okay, so I think both of those work really well as examples. You might have this kind of situation. Whoops, I should probably make that actually touch zero. All right, so that might be a case where you look at this on the velocity graph and you're like, oh, nothing changed direction. It's like you thought about changing directions, but you didn't change direction. Okay. Alternatively, it could be, as Graham said, when we're looking at the negative to negative, it could be something like this. Okay, so this is a negative and negative y values. This is negative velocity, and this one is positive velocity. I know you've been plagued by graphs in the sense that you have to read what axis you're looking at. Okay. And a lot of times when we say things, we're like, oh, it's positive slope. We're leaving out the most important part of that phrase, which is it's a positive slope when we're looking at a position graph. Okay. And so small phrases like that are really going to change what information we get from the graph. Okay. Now, I do want to point out that sometimes this can look like this, like more like a absolute value-y sort of situation or an absolute value-y sort of situation. But in either case, if all the y values are positive on the velocity graph, we'll have a neither situation. Okay, or if all the velocity y values are negative, then we're looking at sort of a negative tangent or a negative cubic function. Okay. Now, I know this is a lot, all right, which is why we've drawn so many pictures to kind of help us visualize this, okay? I can imagine that this would be a really useful tool during an exam to have pictures of what we're looking at. So before you sort of answer questions, think about matching those pictures, okay? But you'll also notice that we didn't write a lot of words here. And so that would be something that as you kind of go back over your notes and as you're studying, that I would include some words for yourself. It wouldn't hurt to write a few sentences about what each one does if that helps it be more sticky in your brain. Because I think if you can write something to describe this, you actually know a lot more than maybe you think you do, okay? All right. So there is a second theorem. Okay. And this one is not dealing with the first derivative, but it deals with the second derivative. Okay. And there is something called concavity. And that's what the second derivative actually tells us about. Okay. So this time we've only got 2 bullet points, but we've got here that if f double prime of x is positive, then f is concave up over the interval. Flip that statement and you get if f double prime is less than 0, then f is concave down. Okay. We're going to draw less pictures here, but we're still going to draw some pictures because I think understanding what it looks like is really important. Okay. So first picture, let's take a look at what it might be to say that something is concave up. All right. Now, concave up in our brains, I want us to really connect to this idea that it's something that sort of holds water. Okay. If you think about a container that holds water versus one that doesn't, then you might think about something sort of like this, like a bowl sort of situation, right? Now, I think this is easy for students to connect. You're like, concave up holds water, we're good to go. Something that looks like this. Okay, so like a parabola is concave up, all right? However, this is sort of the tricky part for students. You can take parts of this parabola and parts of it can still be considered concave up. For example, I could just say, I have the left half of a parabola. I know if we put water in here, it's all going to spill out the bottom. Okay, I realize that. That's where this metaphor breaks down. However, because this whole shape is considered concave up, any part of it is also considered concave up. Okay, so if this is concave up, then so is this. Okay, so picking the whole parabola or the left half or the right half, in all three of these pictures, if you take the second derivative of the function, you'll find out that it's greater than 0. Now let's change this for what if it's concave down. Okay, so what if instead of using a hold water analogy, we said, ooh, it actually does not hold water at all. All right, then maybe we imagine we have something like an upside down parabola. Okay, that would be considered concave down. But if this is concave down, so is any part of it. This is also concave down, just the left half. Or this is concave down, just the right half. Okay, so just like with the concave up, anytime you have something that looks like it's going to completely spill the water, that second derivative is actually less than 0. Okay. All right, so that's a lot of information. All right, that is a lot of information. I think this graph helps sort of break that up a little bit. Okay, so it's kind of a nice summary graph here of thinking about what this looks like on a graph that is, we could think about this as a position graph. Okay, that things can be increasing and decreasing, but they can also be concave up and concave down. All right, so I'll leave this graph here for you to take a look at. And I'll leave a little note here that it might be interesting to consider the following question. What does the y prime graph look like? Okay, what does the y prime graph look like? Meaning, what does it mean when a function is decreasing? What does that look like on the graph of the derivative? What does it look like on the graph of a derivative for something to be concave up? Okay, what does it look like to be something concave down? But I think if you can put together a new picture of what it looks like for the y prime, I think that's a really great way to synthesize all of the information we just talked about. Okay. All right, so we've gone this whole class. We've only looked at 2 problems and we haven't even applied any of the theorems yet. So let's do a practice problem, okay? All right, so we've got a graph, f of x equals negative x to the 4th plus 4x cubed minus 20. And the task is I would like us to graph this using first and second derivative. Okay, so I've set this out in a step-by-step format for us. And we'll talk about what these different pieces mean. And then we'll move on to a different case where now we're going to be looking at the derivative and how we sort of unpack information from that. Okay. All right, so here's my function. F of x equals negative x to the fourth plus 4x cubed minus 20. So step one, I would like us to find f prime and find the critical numbers for f of x by setting that derivative equal to 0. And we're solving for x using things like the greatest common factor and factoring. All right, so I'll give you a moment to do that and go ahead and find that first derivative, set it equal to 0, do some factoring. Let's see what we get. All right, so let's take maybe like 3 minutes to find that derivative, set it equal to 0, and work on our factoring. If anyone has that first derivative, go ahead and type that into the chat. If you have it factored, go ahead and type that into the chat. You could send that to the whole group or you can send it to me directly. No judgment either way. Ooh. Competing ideas for that first derivative. What do we think? There we go. There we go. Okay, good. Negative 4x cubed plus 12x squared. Love it. Love it. Okay, so here's our first derivative. We're going to set it equal to 0. So negative 4x cubed plus 12x squared equals 0. All right. Yes, great job, Isaac. All right, how do we, oh, make sure there's a cube there though. That might just be a typo. But how do we factor this? I could factor out a 4x. We could do one better. What else can we factor out? 4x squared. Great. Let's factor out a 4x squared. You can factor out a negative 4x squared. Either way is fine. Let's go ahead and factor out that 4x squared. This will be negative x plus 3 equals 0. Okay, so I chose this problem because I want us to remind ourselves that we can always look for a greatest common factor. I don't want us to get to a cubic and kind of panic and be like, oh, I can't factor that. Because in this case, it was actually really just into a linear factor and a quadratic. Okay. All right, so what do we get for our x values that make this 0? Well, we've got x squared equals 0, and we've got negative x plus 3 equals 0. Okay, so it seems like I have one critical point at x equals 0 and another critical point at x equals 3. Okay. So any questions about how we found these critical points? All right. We've found these points before, right? It's been disguised as the question that says, when is the particle at rest? When is the velocity 0? All those different ways of asking it, but this idea of a critical point is just saying this is where the slope could be 0. But this next part is what tells us, is it a maximum Is it a minimum or is it neither? Okay, so here's what we mean by a sign diagram. We're going to draw a number line. And on this number line, we're going to mark off our critical points. Okay. Only numbers that need to go on there are your critical points. They should be in order from smallest to biggest. Okay. And then we're going to pick some numbers. All right. So let's do this. I would like you to pick a number that is smaller than 0. All right, everybody pick their favorite number that is smaller than 0. Okay. Now, what I want to know is the slope before 0 positive or negative? So if I'm interested in the slope of this region, should I use the original function or the derivative? Yeah, anytime I want to know about that slope, I better be using the derivative. Okay, take your favorite number that you chose. You're going to plug that into the derivative. Okay, I don't care what the number is. I care whether it is positive or negative. All right. So some folks pick -1, some folks pick -9, some people were fancy and picked -0.5. I don't care what number you picked. Tell me, when you plug that number into your derivative, do you get a positive value or a negative value? Positive. Good, good, good. Okay. So that means that all the slope before x equals 0 is positive. So we're just going to put a plus sign above that region. Okay. All right. Now we rinse and repeat. I want you to pick your favorite number between 0 and 3. David can be fancy. He can say, I'm going to pick 11/14, whatever you want. Okay. But pick a number between 0 and 3, plug that into your derivative because we care about slope, and tell me what sign your answer is. We getting positive? I would agree with that. So I'm going to put a big plus sign and a circle above that region. Okay. And let's do that one more time. I want you to pick your favorite number that is bigger than 3. Could be as large as you want. Plug it into the derivative because we're interested about slope. Tell me about the sign of your answer. Yeah, negative. Good, good, good. Okay. So this is our sign diagram. Okay. We took our critical points, we put them on a number line, and then we picked numbers from all the different regions and determined whether the slope was positive or negative. Okay. Now, the analyze your findings part. Okay. At x equals 0 and at x equals 3, I want you to go back into your notes and tell me, do we have a maximum, a minimum, or neither? And be prepared to justify your answer. Like, how did you know that it was a maximum? How did you know it was a minimum? How did you know it was neither? Okay. Okay, so it looks like we've got a neither for x equals 0 and a maximum for x equals 3. Now, I'll tell you that when I work through these questions, especially if I don't have notes handy, even to this day, I'll just draw a quick picture. And here's what I mean by that. So if I'm thinking about this one, like what's happening around 0, I know it goes from positive slope to 0 to positive. So then I know this is neither. Okay, so I can go back to my notes or I can draw a quick picture. Either way, as soon as I've drawn the slope, I know what it looks like. Okay. Similarly, at x equals 3, I can say I want to draw a picture that has a positive slope and then it changes to a negative slope. And so positive slope to negative slope means that I have a maximum. Right? So the part in the pink to the right, that is sort of your analyze your findings. All right. And if I say like explain your reasoning, I'm looking for you to say this is a maximum because the slope goes from positive to negative. Or this is neither because the slope goes from positive to 0 to positive. Okay. It doesn't have to be a long explanation, but you have to bring back some of that concept. All right. So now we know we've got a neither, we've got a maximum. All right. So let's go on to that second theorem, which talked about concavity. All right. Now, what we're going to do here is we're going to find f double prime. We're going to, new word, find the potential inflection points for f of x by setting f prime of x equal, or f double prime of x equal to 0. So let's work with the mechanics first. All right. The mechanics meaning let's find f double prime of x. So let's go back to our derivative. We're going to take another derivative. And once you have that second derivative, type that into the chat. What do we get? Negative 12x squared plus 24x, good. Negative 12x squared plus 24x. All right, we're going to set this equal to 0 and we're going to factor. And so while I'm writing this, think about what you would factor out as your greatest common factor. All right, and remember the key word here is the greatest common factor. I would agree with Umar, we've got a 12x. That'll leave us with negative x plus 2 on the inside. All right, let's find those x values. We've got 12x equals 0, which means x equals 0. Or we have negative x plus 2 equals 0, which means x equals 2. Okay. Now, here's what we found here. We have found potential inflection points. Okay, potential inflection point. What an inflection point is the moment when something changes concavity. Okay, let me say that one more time. An inflection point is the point at which the concavity changes. For example, if I had something like this, all right, like a graph like this, I think we would agree that this part is concave down, right? And that this part is concave up. But when does it stop being orange and start being purple? Okay, that is what an inflection point is. The moment it stops being orange and it starts being purple, those are inflection points. Has anyone ever heard of a phrase, point of diminishing returns? Okay, it is businessy, right? So if you think about having a business, right, and you are selling some product. So actually, let's go back to that car rental example we had from knives. Yes, you could be selling knives, right? So you're selling knives and you're like, well, I could work a 5-hour day and sell this much. And if I work a 7-hour day, I'm going to sell more. But if I work a 15-hour day, I might sell more, but it might not be that many more knives because maybe people are sleeping, so not that many people are awake for me to sell to. Or maybe I'm just kind of tired, and so it's not as good for me because I'll be tired the next day. Either way, you start to make less profit, okay? So there's sort of a fine point where you're like, okay, things are going well, oh, things are going bad. And at some moment, I know that it's just going to continue to get worse. It's not going to get better in the foreseeable future. That point at which it changes is called the point of diminishing returns. Meaning, when is it not going to be worth it to continue to put in that effort? That's what we consider a point of diminishing returns. That point is an inflection point. Okay. So it's not necessarily where you make the most amount of money. It's not where you've already hit rock bottom, but it's sort of somewhere in between there. Okay. All right. So we can make a sign diagram just like we did with the F prime, and then we can analyze our findings. So this time I'm going to put on my number line my potential inflection points. So 0 and 2. Let's do the same thing. We're going to pick a number less than 0. We're going to pick a number between 0 and 2, and then we're going to pick a number bigger than 2. Where are we plugging these numbers into? We're plugging them into the second derivative, okay? We're plugging these numbers into the second derivative because the second derivative tells us about concavity, all right? So I'll leave the number crunching to you to confirm, but when I plugged in numbers, I got negative and positive and negative, okay? Got negative, positive, negative. Here's what this means. F of x has 2 inflection points. At x equals 0 and x equals 2. Okay. At x equals 0, it should look something like this: concave down to concave up. All right. At x equals 2, it's going to go concave up to concave down. All right. So negative means concave down, positive means concave up. So mechanically, this is what we've done. We found some critical points. We determined whether they were maximum, minimum, or neither. We found some inflection points. We determined whether they were concave up to concave down or the other way around. But what we're doing now is we're going to string all of this information together to sketch a graph of f of x. Okay. So sketching a graph for f of x. We're just going to lay out a grid, x and y, and we're going to mark off all the important x values we saw from above. So 0, 2, and 3. Okay. So 0, 2, and 3. Now, from above, we know that there is a maximum at x equals 3. So I'm going to go ahead and put a point up here because I know this is a maximum. All right. Now we have inflection points. Those are a little bit trickier to draw. Okay. So I know that at x equals 0, the slope is 0. But it's one of those, let's see what we did. It went from positive to positive. So I need to have a function that's going up, it levels off, and then it keeps going up, just like this part. Okay. So let's go back down. I know it's got to have a positive slope to 0. All right. Now this piece that I just drew so far, this piece that I just drew so far, is that concave up or concave down? That's concave down, exactly. It is half of what we said like an upside down parabola is, but it is still part of it, so it means it's concave down, okay? That makes sense because my second derivative was negative. Second derivative is negative, means concave down, okay? But at x equals 0, I have to suddenly make this concave up. So it flattens out and then it kind of looks like this. All right, see how it changed to now it's part of something that is, we could say, holding water. All right, so this part is concave up. And then at x equals 2, it changes again to concave down because we see that f double prime is negative. And so it's going to change to concave down. And then we get to our maximum. If you graph this function, the original function on Desmos or some sort of graphing platform, you should get something very similar to this, okay? But I do expect that if we're graphing these by hand, that they look a little like Frankenstein-esque in the sense that they're sort of all the pieces of information we've gathered stitched together, okay? So how are we doing out there? I know this is sort of a big meaty problem. Any questions? It is. It's very, very applied abstract, if that makes sense. I think it is both abstract and applied.
I have a quick question again, if that's okay.
Yeah, absolutely.
I don't know if it's just my computer. So there are 2 inflection points. So one at x equals 0 and one at x equals 2. So on the graph changes directions at those points, right?
No, it changes
Like,
convectivity. It doesn't change direction because my slope didn't change. Like my slope is still positive and positive. Because there was no inflection point. So at 3, 3 is bigger than 2. It means that it's concave down that whole region after 2. Yeah, it's all concave down after 3, exactly. Or after 2, exactly. Mhm. Okay. This is a really tricky concept. All right, it is a really tricky concept. I would encourage you to spend a lot of time on this between now and the quiz, but particularly the exam as well. So I think being able to tie it all together like this is really important. Okay, it's one of those where you can't just kind of know one piece and you don't know all the other pieces. You kind of have to know all of the pieces and how they work together. Okay. Yeah, Thea, no worries. What was your question?
sorry.
I
My
know.
question was if at those points at 0 and 2,
Mhm.
there are inflection points, but I don't think I quite understand what inflection points are. So can you please remind me of what that is? I think I missed it.
So an inflection point, maybe if we just drew a sort of bigger picture, let's say we had something like this. All right. I would say that this function is concave down for like, whoops, for like this part. Would you agree that that's concave down? Okay. And would you also agree that like this part right here is concave up? Okay. When does it stop being orange and start being yellow? I don't know exactly where it is, but it looks like it's somewhere here, right? That's the inflection point. Okay. Great. And so we could kind of keep going and color coding. This part is concave down, but at some point it changes to concave up again, and then it's concave down, and then it's concave up, right? And so every time we change colors like that, that is where we have an inflection point, okay? All right. Will the inflection point always be the middle point from one critical point to the other? It is not always. It is a lot of times in some of the examples we see at this level, but I think that's not a fair assumption to make for all functions everywhere. Because one side might go up more steeply, I know, and the other one might sort of take its time flattening out. So we can't always say that it's halfway in between, okay? All right. I'd love to get through some more examples here because we do have questions like this on the quiz. And also I think it will continue to help synthesize what we've been learning so far. okay? So we have this graph, okay? And we want to notice this be a velocity graph. It is not a position graph. I know it's just like one little prime symbol, but if you miss that prime symbol, every answer you write down is wrong. Okay, so scan through, make sure you read the question carefully. What kind of graph are you looking at? Okay. This is a graph of f prime or velocity. And so in these cases, what you see is not what you get. Okay, meaning question 1 says, where does the graph of f of x have a local maximum? And if you go ahead and write x equals 1, I know you didn't read what the axes are, okay? Because x equals 1 is a maximum on f prime. It is not a maximum on the original graph. Like, we don't know what the original graph looks like, but we have to answer questions about it, okay? So this is wrong because it is the maximum of f prime of x, not f of x. Okay, so it's so wrong that I'm going to leave it there so that we remember not to do that. Okay. All right. Tell me what you know about a local maximum. What are the slopes on either side of that maximum? Like, what's happening? Yeah, has positive to 0 to negative slope. Right? A maximum on f of x has positive to 0 to negative slope. All right. 1 is not the right answer. Step away from the idea of slope because it is, let's replace this word slope with derivative. All right. So that is the new layer here. We're looking at the maximum on the original graph, which we don't see, but it means that the velocity or the first derivative has to go from positive to 0 to negative. Where is that point? That goes from a positive to 0 to negative f prime. Indeed it is. X equals negative 2 goes from a, this is a positive f prime, and it goes to a negative f prime. Okay. So let's switch the question now. Where does the graph of f of x have a local minimum? And I'm going to write down 2 answers that would be incorrect. X equals negative 1. What's the other wrong answer? 3. Okay, these are wrong because these are the min of f prime of x, not f of x. Okay. Instead, how can we modify this sentence to say that we're looking for a minimum? All right, so a min on f of x has what? Okay, so it goes from negative to 0 to positive f prime. I don't see anywhere on here where it goes from a negative value to a positive value. If I extended the graph right here and it kept going, then we would have a minimum at x equals 4. But the graph stopped, so we don't know what happened there. Right? It does, however, have some critical points that are neither a maximum or a minimum. Where might those be, and how do we know? One and 4. Good. Okay, so we can say that at x equals 1 and x equals 4, f of x has a critical point that is neither, because f prime of x does not change signs, meaning it doesn't go from the positive to the negative or the negative to the positive. Okay. So these first 3 questions here are all about reading f prime. And our next 3 questions will be talking about f double prime. Okay. Let's take a look at these next 3 questions. Where does the graph of f of x have an inflection point? Where is the graph of f of x concave up? And where is the graph of f of x concave down? Okay. Well, we know that f of x has an inflection point when f double prime of x equals 0. What does f double prime equals 0 look like on f of x? Like if I say f double prime equals 0, what am I looking for on f prime? Okay, that's exactly right. This corresponds to the extrema of f prime. Okay, and so if we go back up to our graph and we say, where are there maxima and minima? We can see 3 of them at x equals -1, x equals 1, and x equals -3. Okay, so we can say that therefore x equals -1, 1, and 3 are inflection points on f of x. Okay. Well, if we're looking for the extrema, and that tells us the inflection points, then here's what we know about concave up. F of x is concave up when f double prime of x is greater than 0. And this corresponds to positive slope on f prime of x. Yeah, exactly. So you're going to look for everywhere where it has a positive slope. And if I were to modify this sentence for concave down, I could say it is concave down when f double prime is less than 0. And this corresponds to the negative slope on f prime. All right. Now I'm writing all these words because I know that this is really tricky. All right, because you're looking at it, you're like, you're telling me that the highest point on this graph is not a maximum. Like that messes with your brain, right? But I think you really got to bring it back to what do you know about slope and how all the different derivatives relate to each other. And so on this particular graph, we'll get -1 to 1 and 3 to 4 as places where we have positive slope. And negative slope will be from -3 to -1 and from 1 to 3. All right, so I know we've got about a little bit more than 10 minutes left. What I'd like to do is to go through one part of example 3 and one part of example 4, okay? All right, so example 3 sort of brings it back down a little bit. All it says is use the first derivative to determine the x value of any extrema, okay? And so all we're going to be doing here is going ahead and finding that first derivative, setting it equal to 0, and solving for the x value, okay? We don't need to do a number line. We don't need to do any of that. We're just looking for critical points, all right? So let's do part B here, all right? If I want to find g prime of x, then the rule that might come to mind here is product rule, okay? And so that's why I'm picking B to go over, just as a reminder that sometimes we still need product rule when it's a product, okay? And so if we set up our product rule, we have u equals x squared minus 3, du equals 2x, v equals e to the x, and dv also equals e to the x. All right. Now, when we plug those all into our product rule, we get u times dv plus v times du. And I notice that I'm going to want to set this equal to 0, but while I'm simplifying the other side, I might also notice it has a common factor of e to the x. And so I'm going to factor that out, e to the x. What's left inside? X squared minus 3 plus 2x. All right. And again, the reason why I'm choosing this example is because this is actually a really valuable thing that helps out in a lot of sort of future math classes, is reminding ourselves that e to the x can never equal 0. It has a horizontal asymptote. It never equals 0. So the only thing we need to consider is when does this polynomial part equal 0? So we'll have x squared plus 2x minus 3 equals 0. We factor. and we get x equals -3 and x equals +1 as potential critical points. Okay. So bringing back some of those old derivative rules from chapter 3, knowing when to use what, doing it correctly so that you can interpret those results. All right. So when we say first derivative test, that's all we're looking for. No number line, no anything else, just find that first derivative, set it equal to 0. Okay. Now, example 4 is similarly thinking about just using the concavity test. So that concavity test is not the first derivative, but it's the second derivative. Okay, so we're looking for the second derivative, and when does that equal 0? All right, so let's again pick B. I got to find my second derivative, and to do that, I got to find my first derivative. So what is that first derivative? If I have 3 plus sine x, what is my first derivative? Yep, we've got cosine x, good. And the derivative of cosine x gives us negative sine x, good, good, good. Okay, so here we've got our second derivative. So now I'm gonna take the second derivative and set it equal to 0. I can divide that -1 away. I get sine x equals 0. And thinking about all the values that make that true, let's just go one time around the unit circle. We know that at 0 it equals 0, and at pi, sine of pi is 0. Okay, yeah. Let's add that in there, that just one time around the unit circle. Okay. All right. So folks, I think this is a good place to stop. All right. As you go over this information, and I would do it sooner rather than later while it's kind of fresh in your brain, I would go back and take a look at example 3A. That's another one you can work through on your own. Taking a look at example 4A, we divided by -1. Yeah, exactly. Okay. Now, these are the kinds of things that, an instructor might not write, but as you're taking your notes, leaving notes for yourself like this, you divided by -1 might be might not be a bad idea. Okay, so sometimes, especially in my own classes, I know that I often write down more than what the instructor is actually saying, and that can be really helpful. Okay. Now you'll notice that as the semester and as the year has progressed, this is something I do less and less of, okay? Intentionally so, not because I'm like, oh, you should know it by now, but because I want you to really practice those strategies, okay? As you move forward, it's about being successful, not just in this class, but in your other future classes as well, okay? There is also one more practice problem here, number 5. I think that's a really good one to go over. Should be very similar to question number 2, because it's a graph of, you guessed it, f prime. So I'll leave that one there for you folks to go over on your own as a way to kind of check for that understanding. Okay.